produce useful products, such as fuels, solar fuels. So designing materials to harness sunlight for various applications requires knowledge of how light interacts with matter at the nanoscale, so-called nanophotonics. And today, Harry will tell us about new horizons and grand challenges in nanophotonics. So, what did you do?
One off.
Sorry about that.
Okay. I got the mic pretty heavily here. If somebody can turn this down. Okay. Okay, good. So I'll go ahead and get started. Is that, okay, that's better. Fantastic. Okay, I'll move my mic back up here then. Okay, good. So I'd like to tell you about 3 topics today. This is a diverse department, a diverse audience. So I thought I'd try to span a number of interests of mine. As you can see, we're looking here at the sun shining down on the Earth, very without prejudice against on all of the world, just like it is here in Atlanta today. So we're going to start our story down on Earth, where we're going to look at light emission mechanisms of materials, 2-dimensional materials. Then we're going to talk a little bit about artificial photosynthesis, and then we're going to come back up into the heavens and talk about nanophotonics as a platform for generating future spacecraft. So I'll begin. Let's see. Okay, so I guess this guy there. Okay, so just to set the context for students, the field of photonics is one that really is around us every day. It's in the forms of new energy that are being generated, lighting in our homes and places at work, displays that you look into every day. And in fact, as we begin to look at the connection between biology and vision, just the fundamental issue of perception itself is a hopefully this money. Okay, so maybe that's a little bit better. And of course, in photochemistry, sunlight and light is interacting with our atmosphere. And of course, light is used as the tool for communications and interrogating the micro and nano world. So if we think about what a revolution we're currently undergoing in nanophotonics, it's helpful and insightful to go back and look at the first optics revolution. The first optics revolution happened when the Dutch and Italian lens makers ground their ground lenses in quartz. So, for example, Galileo Galilei, who of course famously got in trouble with the Vatican for proposing a revolutionary and heretical view of the solar system, developed a telescope which allowed him to, using round lenses and dielectric optics, to observe mountains and craters on the moon and the Milky Way and spots of the sun. This is in just in the beginning of the Renaissance, really quite a spectacular development. And you can also see Van Leeuwenhoek, if you ever have a chance to go to the Netherlands, in Leiden, there's a beautiful museum called the Boerhaave. You can see this first microscope that was developed by Van Leeuwenhoek, which features a little round lens there made of quartz. And that lens opened a completely new vista into the micro world. And for the first time, microscopic organisms in living cells were seen. In fact, red and white blood cells, yeast cells, bacteria were imaged. And in fact, the revelation that there were bacteria both in humans and in the environment spurred all across Europe the growth of medicine and public health. And in fact, it ultimately resulted in transformation of the way cities were architected to cope with the knowledge of the public health challenges of dealing with period. So a staggering impact of this first revolution in optics. So if you think about the length scales, the Dutch lens grinders ground lenses that were millimeters in scale, and the optical function came from the curvature that they imparted to what is basically a homogeneous material, quartz. Constant, uniform refractive index, transparent. But of course, now we're able to make nanoscopic, microscopic things. And so we now make photonic structures like these single mode fibers or these disc lasers that are in the scales of hundreds of microns down to tens of microns. In fact, when we start to architect things on the scale of the optical wavelength themselves, we can produce 1, 2, and even 3-dimensional standing wave modes that form new types of cavities, photonic crystals. And in this, but we can also know from our experience in technology that electronics, which really developed a lot of the technology which allows us to make these small structures, is currently able to make things much smaller than the scale of the wavelength itself. In fact, you have to use an electron microscope to look at the smallest transistors inside. If you could pry open your phone and look at the chips inside, you wouldn't be able to see them by eye. And so optics, for a long time, was unable to get and access this regime, at the sub-wavelength regime. And so a key element of that was the introduction of metals, which have extraordinarily large permittivities, and which enable a strong scattering and enable us to get into this realm where we're in the realm of biological objects, somewhere between the scale of a virus and DNA, so in the tens of nanometers range. And so that was really where optics first came into the world of the nanoscale. And the ability to tailor light at the nanoscale has allowed, by control of the phase and amplitude of scattering and the frequency selectivity, to project images using wavelength and subwavelength scale structures. Here's an example of structural color. This image is made of tiny little resonant structures that are sub-wavelength, and they're resonant at different wavelengths, and each of them has been architected at a different size and shape so as to reflect light at different colors, rendering this entire image. And if we put nanostructures together, very often we can generate strong fields in the interstices between these very high permittivity objects in free space, where we have the low permittivity of free space. And that enables us to achieve very strong confinement of light that wasn't previously possible. And particularly in metals, we have the feature that metals are polarizable. They have many, roughly one free electron per atom in the lattice, and in a metal particle. When we now excite a metal particle with a field that it resonates at the natural frequency for electron oscillation in the metal, we approach the so-called plasma frequency of the metal. We see a resonant increase in the amplitude, so that will produce a resonant increase in both the absorption and scattering components of the extinction, and it will also produce a very strong change in the phase of the scattered wave as we go through the plasma resonance. And in fact, you can see from this very vivid image of showing the flux of the field lines at the resonant frequency for a small metal particle, that the optical cross-section of a metal particle can be many times its physical cross-section. So this really shows and illustrates the power of resonances in nanophotonics. So what is emerging and what is generating a new revolution in nanophotonics, I don't have time to cite all the examples today, is the combination of materials, plasmonic materials like gold and silver, and dielectric materials like silicon, together with materials that are emerging. For example, some examples are the 2D and layered materials, which have the intriguing properties that because they're so thin, we can apply electric fields and change their carrier densities. We can dope them electronically, change them from being semimetals into semiconductors, or from semimetals into metals, and we can take semiconductors and make them to be essentially metals. And so changing dramatically their permittivity. So we can generate resonances with these structures and generate tunability with these kinds of structures. So the first topic I'd like to tell you about is tunable plasmonic interactions in graphene. Graphene, of course, is the granddaddy of them all of 2D materials. And I'll say a few words about perfect absorption near field modulation and spend most of my effort in this talking about direct spontaneous emission. And these are the talented team of students and postdocs. Most of them have now moved on from Caltech, who performed work. And so graphene in particular is a material that has negative permittivity in the infrared. And as a negative permittivity material, a single monolayer of graphene can support surface plasmons, can support electromagnetic waves that couple to the electron density oscillations. And the thing about graphene is that it is a spectacular plasmonic material. It has, for example, the feature that when excited with a free space wavelength in the infrared regime, I can now produce wavelengths, plasmon wavelengths, in the tens to hundreds of nanometer range. So it has the effect of shrinking the wavelength by a factor as great as 100. And that is related intimately to the extreme confinement of the electromagnetic mode in graphene to this sheet. And so we can understand this, and for example, if we now move the Fermi level of graphene away from the Dirac point where it's a semi-metal, and we dope it, so to speak, by moving the Fermi level up, the electron dope it, then we make it more metallic. And if we excite with photons below this inner band threshold, shown here from this K point to this K point, so I can get ordinary inner band absorption from a filled state to an empty state here, but these states are filled, so if I excite with the lower photon energy, I get intraband transitions that couple into plasmons. And so this combination of materials resonances that I can generate with graphene plasmon resonances that are tunable. In fact, I can use the electrostatic control of the gate and the Fermi level position to tune the resonant frequency of the material. I can combine that with the geometrical resonance. Say I have this little patch antenna, a metal patch on top of a ground plane. And by combining these two together, I can make actively tunable light devices. And I'll just give you a couple of examples here. This is some recent work from Se-In Kim, Victor Gerard, who showed that by taking a surface in which tiny little slits are cut in a metallic grating, and ribbons of graphene are placed within these slits, 100 nanometer wide slits, that it's possible by tuning the carrier density in the graphene so as to be resonant with the infrared radiation, to tune the absorption off resonance from less than 10% to more than 97%. So I can make a material that goes from essentially being unabsorbing, despite the fact that it has composed of metals, dielectrics here, off resonance, and to being fully absorbing. And essentially all of the absorbed power is being absorbed in these tiny ribbons. And so you can generate now absorption in a surface that is covered with less than 1% of the monolayer of graphene. That 1%, or excuse me, 10% of the monolayer of graphene is absorbing 97% of the incident radiation. So this is a tunable effect. We can also, for example, in the case where graphene layers are brought into intimate, near intimate contact with one another, not quite physical contact, but close enough that their electromagnetic modes can interact. And in this regime, it's possible by modulating the Fermi level of one sheet relative to the other to make them go from off to on resonant coupling and to make a thermal switch, something that electronically, as I change the voltage, changes the flux of heat from one layer to the other. And this has the effect then, because this is in the near field, enabling heat fluxes that exceed that of the far field radiative limit that the Stefan law would permit. And but I want to spend some time talking about ultra-fast control of graphene plasmons. And what we know about ultra-fast excitation of graphene, you might think that almost everything had been known about graphene. It's a spectacular material. Scientists have been working on it for more than 15 years. What's new about graphene? In 2016, Dmitry Basov's group showed in near-field microscopy that excited graphene emitted infrared radiation, light in the infrared, whose dispersion characteristics were remarkably like those of graphene plasmons, but where the attributable temperature of the electrons was much above that of the lattice, as high as several thousand Kelvin. And so these were near field, and there were no far field observations. So one of the questions that we have is, although we saw this intriguing observation of hot plasmons, is there a mechanism by which they could potentially emit mid-infrared radiation? Mid-infrared is a very challenging wavelength regime. We were just talking earlier today about the quantum cascade lasers, which are available at mid-infrared. And of course, you can make a laser, you can make it operate at a frequency that's determined by the quantum cascade infrared transitions, but it would be very desirable to have a tunable broadband infrared source. So let's, for a moment, reflect on the carrier dynamics. If I take an ultrafast pulse and I excite graphene, I'll first excite promptly here on this Dirac cone where states are filled here, and here I've depicted this as a whole-doped material, where I've excited now using this frequency pulse from these completed carriers from these states and populated these states on the upper Dirac cone, generating excited electron states and Hall states that are very non-thermal, highly non-thermal. In fact, they not even no attributable temperature. Within a few tens of femtoseconds, these will begin to relax. They'll have internal electron-electron scattering that will carrier-carrier scattering that will give rise to thermalization of these carrier distributions. And on the time scale of 100 femtoseconds or so, we'll see other processes that will begin to emerge, like optical phonon emission and Auger recombination. And it's at this time scale that we begin to see a tail and something that looks like a Fermi-Dirac distribution, although hot, which we can interpret then as an electron temperature in the range of a couple thousand Kelvin. And then, although it has been theoretically proposed, it had not yet been previously observed experimentally, another channel that in fact could in principle compete with Auger recombination and phonon emission, both of which signatures of which had been previously experimentally determined, is plasmon emission, not plasmon absorption, which I just talked to you about a moment ago in the tunable graphene structures, but these excited carriers here, excited single particle states, recombine and emit a plasmon into the graphene sheet. And then, of course, the other processes that occur on the few picosecond time scale are acoustic, low energy phonon emission, and then finally, if I wait a long time, the entire sample will cool back down to its ambient temperature. So we probed these experimentally, these excitations in graphene, using a type of heterostructure in an infrared spectrometer, Fourier transfer infrared spectrometer, with ultrafast excitation inside the FTIR through a transparent back window here made of indium tin oxide. This indium tin oxide layer allows us to gate the graphene and change its Fermi level position, which turns out to be quite important in understanding the carrier dynamics. And in some of the samples, we put little tiny gold nanoantennas on the surface to outcouple light into free space. So the first basic observation that we see in the mid-infrared, if we simply look at the sample before we turn on the laser, we see this at a temperature of 95 degrees C, and this is the steady state temperature that the sample will get to when it's irradiated by the megahertz pulse train. We see thermal emission here, peaked at around 9 microns, black body-like emission. But when we turn on the laser, we see an additional contribution here in the 5 to 8 micron range, with this about a 30% more radiation coming out, and a radiation component that is Fermi level dependent in its emission intensity. So if we were to compare, for example, what would happen if we turned off the laser again and then looked at it, and this is actually a slightly different sample, and we would see a tiny modulation of the emission in the infrared. This is actually not coming from the graphene. We know from refractive index measurements and calculations is actually coming from the rest of the sample, from the ITO portion of the sample. This is the portion where of the spectrum where the graphene dominates the emission, and we see no change in thermal emission upon modulation of the Fermi level. So there's something going on, and if we simply look at CW laser excitation at the same intensity, same average intensity as under ultrafast excitation, we can see something that looks a lot like thermal emission, and very unlike what we saw here in the pulsed excitation. So what's going on here? So if we were to apply a conventional way that you would look at the electron-phonon coupling, a two-temperature model, and you made a prediction based on the two-temperature model, what would you expect the dependence of the emission to be and its dependence on the Fermi level position? What you would find actually is that while we see increase in radiation with increasing Fermi level position in our experiments, the two-temperature model would predict that there would be a decreasing intensity with increasing Fermi level position. And we would see a broad peak here. There's some signatures that are similar, but the sign of the dependence of the emission intensity on the Fermi level position is opposite its sign. So this suggested that this was due to plasmon emission and not due to ultrafast photoluminescence or due to a pure thermal emission process that's being by a structure whose emissivity is simply being passively modulated at steady state. So you might ask, okay, but is it really plasmon emission? What's a really smoking gun piece of proof that it's due to plasmon emission? And I know, for example, if I pattern the graphene into ribbons, the ribbons themselves act as little dipole resonators. They only act as dipole resonators when the polarization is horizontally oriented or perpendicular to the long axis of the ribbons. So I should couple into a dipole plasmon mode of these ribbons. And in fact, I see that in calculations and in experiments in absorption. So the question is, do I see that in the emission characteristics? If I look at CW laser emission, I don't see CW laser pumping, I don't see it. If I look at the pulsed laser emission, I see it. And I see that if I rotate the polarization, this is actually the smoking gun, then the localized dipole plasmon resonance in the emission disappears. So this is clear evidence that this is coming from plasmon emission. So what are the implications of this? So I've told you about infrared emission. By the way, we're able to compute a non-equilibrium dielectric function, setting the permittivity to 0, and then calculating the non-equilibrium portion of the polarizability that you add on to the ordinary steady-state thermal equilibrium polarizability, and to calculate the dielectric function due to these hot plasmons. And what you see, for example, is that whereas in thermal equilibrium, the dispersion relation looks like this, the relationship between wave vector and frequency. I have down here interband excitations when the photon energy is high. And then this red line indicates the dispersion relation. So for passive lossy material, this is well known in the plasmonics community. And what I would see here is that this would correspond to materials that are always lossy. They're a little bit lossy when they're in the plasmonic regime. They're now quite lossy when they're in the interband regime. But in the photoinverted state, where I've created these hot carriers, there are actually two regimes. There's a regime down here where there should be, for small wave vectors here, gain, and this is of course a temperature dependent, or time dependent, and then loss. And so I see a transition from gain to loss as a function of wave vectors. So the dispersion relations, both the real and the imaginary part, look quite different. And in fact, the differences are quite manifest in the imaginary part. So what it basically says here, the inversion allows a reversal process of absorption. In other words, this material has become active. It has a negative imaginary part of its permittivity, and it's giving rise to emission. As I'll show you, we believe this is strongly due to spontaneous emission, but we also believe that there is a regime where we could see stimulated emission, or gain. In fact, if we do those calculations and we use this non-equilibrium dielectric function model, you can see here for different Fermi level positions and for different times as the gain, the imaginary part of the dispersion relation, which is positive indicating gain. And we see, in fact, and by the way, the spectral dependence here that we see It looks like it's sloping down along wavelengths, whereas it looked like it was sloping up in the experiments. If you now correct for the surface roughness, because in our experiments we don't detect in the near field, we're detecting the far field radiated plasmons that have outcoupled into free space, the spectral dependence of the outcoupling due to the roughness of the graphene is shown here, and so when you put those two things together, you see something whose spectral dependence is similar to that as seen in the experiments. The outcoupling efficiency in this case is about 10 to the minus 4, 1 plasma over 10,000. Now, if you go back and ask, what's the spectral flux of this, you see that this is a very, very bright beam. So this is several orders of magnitude higher than even the hot plasmons. Like I heat a material to several thousand Kelvin, and I radiated plasmons, I radiated black body emission from that sample at several thousand Kelvin. I would see here that the brightness of the spontaneous emission could be much higher. So what this basically says is that graphene could be, in this pulsed excited form, the basis for a very broadband and tunable source of spontaneous emission, and possibly also if we can pump and then detect light at very early times, we may also be able to see the operation of a spacer, or in the case where we have some efficient outcoupling mechanism, a plasmonic laser. And so we're currently doing experiments at the moment, probing at very early times relative to the laser pulse, where we expect the ratio of stimulated emission to spontaneous emission to be greater than 1. So the story as of now is that we see bright spontaneous emission. And by the way, this brightness is far in excess it's comparable to the brightness of a quantum cascade laser, for example, but it's very broadband. It's pulsed, but it's, I think, quite an interesting light source. So I want to shift gears now and talk about generation of fuels from sunlight. And this is an enterprise that is a large-scale activity at Caltech in the Joint Center for Artificial Photosynthesis to harvest light from sunlight in solid-state heterostructures made of semiconductors and whose surfaces are coated with catalysts that take the charge carriers generated in semiconductors and perform oxidation and reduction reactions, generating, for example, oxygen and either hydrogen or reduced products of carbon dioxide. And this is a very interdisciplinary field that requires a knowledge of semiconductor physics, nanoscale nanophotonics, catalysis, and really understanding of defects in all of these materials. The team that performed this work is shown here are talented students and postdocs. And in fact, the artificial photosynthesis that JCAP is pursuing, this is a large team of people with more than 30 PIs and 120 researchers in a partnership between Caltech, Berkeley, SLAC, and the UC campuses, is to essentially follow the admirable example of photosynthesis. Photosynthesis uses photosystem 1 and photosystem 2, for example, to generate reducing protons as reducing equivalents that attach to NADP to produce NADPH, which give rise to the starches and sugars that give rise to give sustenance to plants. Photosynthesis is an admirable process. It's the basis for our the source of oxygen and food supply in our biosphere. It's a relatively inefficient process because the plant's objective is simply viability and sustainability of the plant. It's not to generate as much output product as possible. In artificial photosynthesis, we're interested in developing engineered heterostructures, in this case showing a tandem semiconductor photoelectrode, here essentially very much like a two-junction solar cell, in which we've affixed oxidation catalysts and reduction catalysts, which are depicted at these levels in the band diagram, where electrons are transferred from the semiconductor to these hydrogen evolution catalysts and oxygen evolution catalysts. And so the potential that the semiconductor has to generate is equal to the thermodynamic potential, in this case for water splitting at 1.33 volts, plus the overpotentials to drive these reactions. That's essentially due to the sort of finite turnover frequency of the catalysts to operate at the current densities consistent with the absorption of sunlight. So I want to tell you a little bit about how the story about how this is done and how photonics has come into play. In this case, we have a semiconductor heterostructure of these 3-5 compound semiconductor heterostructures, and we have here a water reduction, hydrogen evolution catalyst, rhodium, and ruthenium oxide, oxygen evolution catalyst. So this entire structure, when immersed in water and illuminated with sunlight, spontaneously, well, with the pumping by sunlight, generates both hydrogen and oxygen. And in a device, we separate these with a membrane, and we separately collect the hydrogen and the oxygen. This is made by a sequential deposition process where we apply catalyst to the front surface and the back surface. So one of the questions is, how efficient is this? So the efficiency of this is determined by how much light can be coupled into the semiconductor. And by taking advantage of some of the things that we know about small particles, for example, small particles have characteristics of their optical properties which are dominated when they're very, very small by absorption rather than scattering. And it turns out that rhodium has its main absorption in this very small particle size regime in the ultraviolet portion of the spectrum and very little in the visible. So we use an electrochemical deposition technique to deposit less than 15 nanometer size rhodium particles on the front surface of this structure. And when we do this on top of a titanium dioxide coating structure, and we look at the reflectivity, we see that the reflectivity before and after deposition of the rhodium, which is indicative of the transparency of the rhodium layer, across the visible range from 400 nanometers through the visible and then on into the infrared, is completely transparent. There's some absorption here in the ultraviolet, but it's virtually transparent. So it's a highly catalytically active catalyst for hydrogen evolution, but it's optically transparent. So we can now, operating under one sun illumination, achieve what was set last year as a new world record for solar to hydrogen efficiency at 19.3%. So for calibration, if you have a solar panel on your roof that you or use solar energy to generate electricity, nowadays you would feel pretty satisfied with yourself if you had a efficiency of 19%. In fact, most panels have efficiencies now in the range of 15 to 17% or so. So this is now the efficiency for going from solar photons to hydrogen. So the molecular hydrogen per solar photon. And this efficiency is made higher by the presence of this titanium dioxide layer that acts also like an anti-reflection layer. If we operate at near neutral pH, the efficiency goes down a little bit to 18.5%. And if we apply a membrane that separates the fuel products, preventing crossover of the hydrogen and oxygen, it goes down to just under 15%. So when we started the JCAP project, for example, water splitting efficiencies were in the range of 1 to 3%. So this is an illustration that by design we can actually go to quite high efficiencies. And in fact, in the last 3 years, the record efficiencies have risen from just over 10% to 19.3%. It's sort of a worldwide race to go on. In fact, it's likely that we can get to over 25% using the same kind of configuration. And the device that I showed you here is actually operating at 85% of the theoretical efficiency for this set of semiconductor materials. So we also want to make things other than hydrogen. Nature doesn't make hydrogen as an end product. Nature makes NADPH. We would like to be able to make, for example, in addition to hydrogen, fuels that would be useful, for example, to power our cars and airplanes and so forth, direct fuels like methanol or ethanol or materials like methanol that could be converted to gasoline. In fact, there's a worldwide effort now to find ways to do this using electrochemical, photochemical, biochemical, and thermochemical methods. So one method might be to do this, to use use one of these processes directly operating on a carbon dioxide feedstock, say from a power plant or from some underground reservoir, and supply water and produce these fuel products. Then, of course, you could, another competing process might be to simply generate hydrogen using some process like the one I just showed you, or another alternative pathway. I don't have time to tell you about all of these, but, and then combine them together and use a so-called Fischer-Tropsch reactor to make hydrocarbons and chemicals using this process. This involves building another reactor, it's capital intensive, but it is a possible route. In fact, Fischer-Tropsch reactors have already been implemented at a relatively large scale to do this. Another way you might do this would be to take fossil fuels, methane, which, for example, we have an abundance of natural gas in the United States, to perform something like steam reforming of methane, where we produce hydrogen plus CO2, capture the CO2 for some later use, and then use the hydrogen together in a similar thermochemical process to generate these fuels. So these are all ways that we could generate fuels directly using sunlight or some source of thermochemistry to generate fuels. So one of the challenges in these processes, each of these has their advantages and disadvantages. In JCAP, we're working on these two, on electrocatalysis and photocatalysis. And one of the big challenges in both of these is generating product selectivity. When we split water, we make hydrogen and oxygen. There's nothing else you can make. Those are the only constituent atoms that you have. When you take carbon dioxide and you now reduce it by hydrogenation or electron transfer, you take carbon dioxide and you can make a multitude of different products. You can make methane, ethylene, carbon monoxide, methanol, formic acid. The entire cornucopia of carbon chemistry is open to you. And typically, if you're trying to make one thing in particular, say a fuel like methanol or a gas, a precursor for chemicals, ethylene being a precursor to the plastic polyethylene, then making all these other things is essentially an unwanted side reaction. So we're very interested in selectivity. So one of the key focal areas for science and JCAP at the moment is to develop product selectivity, to make one of these products in preference to the others. So we have many strategies in electrocatalysis that involve atomic scale engineering of the surfaces by controlling the electrolyte environment in the near surface region, adding molecular additives to the surface, controlling the density of catalytically active sites, and so forth. What I want to tell you about is using light essentially as a selectivity agent. Instead of using light just as the engine for photoelectric catalysis, as I showed you just earlier, to actually exploit the excited states of light, here by, for example, exciting in a metal catalyst hot carriers that decay from plasma, exciting hot carriers from plasmon decay, or exciting molecules directly using a plasmonic structure as an antenna at the interface where molecules absorb on the surface. And these, this concept of generating hot carriers is well known. The group of Naomi Halla showed about 8 years ago that it's possible to generate photocurrents whose source is coming from plasmon decay in metals rather than from the associated proximate semiconductor material. In fact, Mark Voskowitz showed that you could put together two plasmonic structures, one that's capable of water oxidation and one that's capable of hydrogen evolution to make a little particle that can split water, somewhat inefficiently, but nonetheless without any external assist. And then, for example, more recently, gas phase selective hydrogenation of CO2 has been demonstrated from the group of G. Liu and Henry Everett in UNC Chapel Hill. So we were quite interested in starting with an understanding of the plasmon decay routes. And to do that, we need to go directly back to the electronic band structure of the metal. And note that we can have band structure, band transitions, decay, which are by a direct or a phonon-assisted process. And these show, for example, the pathways for on plasmonic metals like aluminum, silver, copper, and gold. The blue spikes indicate from interband transitions the probability as a function of incident photon energy of generating carriers at a given energy. You can see, for example, these sharp spikes at negative carrier energy, that refers to a hole, is indicative of the fact that in gold and copper, we should be able to generate hot holes. And in fact, recently we showed in a photoelectrochemical experiment that we could see clear evidence of hot holes being formed. This is the first known example, not a hot electron process, but a hot hole process, where electron hole generation in the metal led to hot hole injection across the Schottky barrier between the gold and the valence band of the wide bandgap semiconductor gallium nitride. That localizes an electron here, which is available to reduce carbon dioxide. And we were able to see, for example, that the selectivity under illumination saw a small but notable increase in selectivity under illumination due to the injection of hot carriers relative to the electrochemistry at the same potential in the dark. And in fact, we found that under other conditions, we could achieve about a factor of 2 increase in selectivity for generation of carbon monoxide over hydrogen. So this is an example showing the plasmonic hot carriers. So I want to finish my talk here by moving back out into space. Okay, so where is he possibly going with this, you might wonder. So I want to talk about something in a serious manner that you might first feel a little amused by, and that is the notion of using nanophotonic structures to generate spacecraft, which can ultimately be propelled at relativistic speed. So this depicts a macroscopic object which is permeated with nanostructures sailing past a planet which is not in our solar system. So how could that ever happen? So I want to first introduce the team of talented students and postdocs that did this work. The work was supported by a private philanthropic initiative called the Breakthrough Starshot Program, which is aimed at building a spacecraft that can reach another star in the lifetime of some of you in the audience. So how would that be possible? Well, let's first think about what we know about optical forces in light. So as long ago as the 1930s, people knew that when you shine light on macroscopic objects, you could induce forces and torques. This paper from Bett showed, in fact, in an aluminum needle, you could see rotation of an aluminum needle due to the torque coming from an optical beam. And more recently, we know we celebrated a couple of years ago the Nobel Prize to Art Ashkin for his work on generating gradient forces in optical beams, so-called optical tweezers, where the gradient force creates a potential that can trap dielectric particles. And using these same ideas that were pioneered by Art Ashkin, other nanophotonics researchers realized that by structuring the scattering forces of objects on a surface, it was possible to impart forces in several directions simultaneously that could stably levitate and trap an object over a surface. And in fact, using negative index materials, like these split ring resonators, it's possible actually to generate forces in the opposite direction of the wave vector of the light, making a so-called optical tractor beam, where the light pulls the object back towards the surface. So these are some illustrations of some of the fascinating things that are possible in generating forces with light using nanophotonics. But all of those are in this size regime, where the structures are small, of the order of a wavelength or so in size. But we're interested in the question of taking a macroscopic object, centimeters, millimeters, centimeters, maybe even meters in scale, so millions of wavelengths in size, and understanding how optical forces could generate stable propulsion of such an object. I'll explain why we would want to do this in preference to an ordinary rocket in just a minute. Maybe some of you know, and we'll actually do a little quiz. But to do this, we care about, of course, understanding the shape of this material. We want to know its permeability and permittivity. We want to understand that if we were to build some of these artificial structures that we know how to build, nanoparticle structures and photonic crystals, how these would exert or modify the forces on large objects. So this is an interdisciplinary field that couples electromagnetic theory, classical mechanics, and essentially mechanical engineering, looking at the mechanical dynamics of the mechanical modes of such a structure. So this is all motivated by the fact that, well, those of us in the nanoscience world have been looking down at our microscopes in the last 15 years. Astronomers have been looking up, and they have discovered a remarkable number of exoplanets, planets around other stars that give us some inspiration that perhaps life could be settled in other parts of the universe, in fact, in nearby galaxies. And in fact, in 2016, in Nature, an exoplanet was discovered, this planet, Proxima b, about 4.2 light years away, so around this star Proxima Centauri, or Alpha Centauri b. And that motivated the idea of developing a spacecraft to reach this distance. So let's think for a moment about using a chemical rocket. If we use a chemical rocket, we know from Newton's first law that the speed of the rocket can never exceed the exhaust velocity. Okay, so you eject fuel from a rocket, the rocket goes this way, momentum conservation, and I reach a final velocity that won't exceed the exhaust velocity. Moreover, the rocket equation is a very forbidding equation. It says the initial mass on the launch pad of the rocket relative to the final mass gives me the change in velocity relative to the exhaust velocity. And it goes as the logarithm here. So that means that I have to have a staggering mass relative to the payload mass. And if I work through the numbers, I can find that the time required for a chemically propelled rocket, like the ones that we use to launch to orbit, to get to Proxima b would be about 70,000 years. So that tries the patience of even the most patient graduate student. But what about if we use light? So think about light as a fuel. So what are the characteristics? What does Newton's first law tell us about light? What could the maximum velocity of the rocket be? Speed of light. Yeah. So we've uncapped the velocity for space travel. So in fact, if you work through the relationship for radiation pressure, you actually have relativistic effects that come into play. Although in principle you could get to the speed of light, the required energy would be asymptotically approaching infinity. So as a point design, the Starshot program decided to aim for 20% of the light speed, which is still in the regime that is where relativistic effects don't come into have a strong impact. The velocity scales is the power times the array size or the sail size divided by the wavelength to the 1/2 times mass to the -1/4. So, for example, if I were to point my laser pointer at an object that weighed a gram, in a week I could accelerate it, like this is about the size of an ant. I could accelerate it if there were no frictional forces to a speed of 1 millimeter per second. So it says I have to go to a much higher intensity, in the case about a megawatt per square centimeter, to accelerate a gram. And so with an impulse at this intensity, and this wavelength for a gram, after an impulse for 1,000 seconds, it's possible to get to 20% of the light speed. That's what the radiation pressure and kinematics tell us. And so that would enable us to travel approximately in 20 years rather than 70,000 years. So this group of people, the benefactor in this is billionaire Yuri Milner, Silicon Valley philanthropist. Here's Freeman Dyson. This is Stephen Hawking. Sadly, he passed away in the intervening time. But this team launched the Breakthrough Starshot initiative to generate the components needed. And so I'll just show you sort of a quaint artist animation of what is imagined here. This is in a high mountain desert where there's very good visibility all the way to Earth orbit. A large phased array of lasers, which would not in fact look like radio telescopes. The artist took some liberties here, but would be trained in a phased coherent fashion on a light sail deployed in orbit, which then sends the spacecraft by radiation pressure from a distance in Earth orbit to approximately a distance of 1 AU, about to the little beyond the Mars orbit, and accelerate to 20% of the light speed. So then this intervening distance of 4.3 years requires the spacecraft to go outside the atmosphere, or outside the solar system into the interstellar medium through the Oort cloud. One of the disturbing things I learned was that the astrophysicists don't even know the density of the Oort cloud within 2 orders of magnitude, but that's another problem that we'll have to address. But we expect that it will exert some frictional losses, but hopefully not substantial in this journey to Alpha Centauri. First, Alpha Centauri, which is this red one here, and then the cooler star in the back, Proxima Centauri, and then Alpha Centauri B, Proxima B is the planet. And so sailing by at 20% of the light speed gives this spacecraft about 40 minutes to take pictures within the resolution of the camera spectrometer mounted on board the spacecraft. Okay, so that's the concept. To develop, use a phased array laser source operating in the 1 to 1.5 micron range on an ultralight scale, square meters in size that weighs a gram, launched to 20% of the light speed. So that requires several miracles to occur. So it requires a phased array laser, and it requires a light sail, and it requires a star chip, a payload that is capable of imaging and spectroscopy. This is the one that is already essentially in hand. It's not, doesn't take too much imagination. If you were to pry open your phone, you'd find that there's a chip inside your phone that handles all the electronics, and another chip which does image sensing in your camera. So you can imagine that, that some of those, if you stripped away the battery and the display, would be of the order of the scale of a gram. And this, in fact, is such a chip that's already been deployed, and it's already been flown in low Earth orbit. So the phased array laser, there's already a team working on this, and it takes advantage of the exponential drop in the cost and increase in the power of solid-state diode lasers using semiconductors. So what I'm going to talk to you about today is the light sail. So what about the light sail? We need to make a material which is square meters in size and weighs a gram. So in order to do that, it means the thickness of this light sail is about 100 nanometers. So what are the characteristics of a light sail material that's 100 nanometers thick that would enable me to efficiently couple radiation pressure to generate propulsion to relativistic speeds? I would need to have a material that has a relatively high refractive index, so I can generate a high reflectivity. I would need to have a sufficiently modest mass density, that I didn't have a large payload weight, and a very low absorption coefficient, because I don't want to inadvertently heat up the sail at the pump laser wavelength, but I do want it to be absorbing and therefore emitting in the infrared, so I can use radiative cooling to modulate the temperature. So these are the cast of materials that seem as feasible candidates, and you'll recognize some of them as 2D layered materials that condensed matter physics people are looking at, and semiconductors that are already in our daily experience, materials like diamond, which are very low absorption. You can have a look at the paper here in October of last year that describes basically the sort of design criteria for such a thing. And so if you ask what sort of photonic structure would give rise to the best acceleration characteristics, it would be the one that weighed the least and had the best reflectivity relative to its weight. So we looked at more than 100,000 possibilities by multi-scale simulations of these nanophotonic structures, so-called metasurfaces, photonic crystals, multi-layer dielectric slabs, single-layer slabs. There were a bunch of solutions near unity reflectivity that weighed about 5 to 10 grams. The best solutions actually, as indicated by the shortest acceleration distance required to get to the final velocity, were lower reflectivity, somewhat counterintuitively, because they had much lower weight. They're about 5 to 10 times lower weight. So that shows that there are viable solutions among these different kinds of structures. So what about cooling? If I now, for example, use materials like silicon as a high reflectivity material in a nanophotonic structure, and then I use silicon dioxide, which is well known to have vibronic, phononic nodes in the 8 to 14 micron regime. So that is a material that's highly transparent at the pump wavelength, but it's emissive and therefore gives rise to cooling in the mid-infrared. And you can show that for known and tabulated and measured characteristics for the absorption coefficient of SiO2 and the absorption coefficient of silicon, that we can limit the light sail temperature to less than 500 Kelvin. Okay, what about propelling this sail using an optical beam? Can I do it in a stable fashion? And the truth is that if I were like Art Ashkin and I used a focused beam to trap a small structure, I could make and trap and stably propel an object, move it around. That's what you do in optical tweezers. If I used a collimated beam of light or a weakly focused beam, and I tried to do propulsion or levitation, it would be unstable. It would literally fall off the optical axis because any perturbation of the position relative to the center of the optical axis or the tilt would give rise to torques that would aggravate its propulsion off the optical axis. However, I could use this beautiful capability of nanophotonic design, in principle, to create a controlled angular dispersion. That is, if I could build structures that, when they tilted off the optical axis, produced restoring forces and torques that move it back towards the optical axis. So for example, if I used an asymmetric grating structure like this, I can apply, I get diffracted orders from a grating. Here's the -1, the +1 order in transmission and in reflection from this grating structure. And I can calculate, and this is for the silicon and silicon dioxide that look like good candidates for the light sail, the reflectivity of the -1 and the +1 orders and their opposite signs of the angle, which means that they exert forces that are restoring. So if I now build these structures with a mirror symmetry around the optical axis, with the left-facing ones on the left and the right-facing ones on the right, I can now create a set of optical forces which is positive in the z direction, in other words, propulsion, where the forces in the x direction are negative for a negative tilt. In other words, if the sample moves in this direction, it will be translated back towards the optical axis. And if it tilts away from the optical axis, it will tilt back. So these are some examples of trajectories. If I start off displaced from the optical axis or tilted, I can get a stable trajectory. If I start way off the axis, then I can't do much about it. But I can find some stable trajectories that work. And in fact, you can define the criterion, and if you look at the Hamiltonian matrix that couples the forces in the translation and the velocity, you'll see that there are negative eigenvalues in this Jacobian matrix that confer stability. So by creating motifs on this light sail with this sort of herringbone-like structure, I can now actually couple with linearly polarized beams to control the angular velocity. And I can actually control the speed of rotation and the speed of the dynamics around all of the axes. So the rotation around the x, y, and z axis, in aerodynamic terms, you call this yaw, pitch, and roll. And this shows for silicon and silicon dioxide the stable oscillation around these different axes. So this illustrates you can have a look at this paper that describes the dynamics, and you can see this is sort of an indication of the trajectory that this thing. So we now have a way, using essentially an unfocused, a very weakly focused beam where the beam waste is immaterial, you can control the dynamics with such a light sail. So we're now just beginning laboratory experiments using dielectric membranes that look like this, that are in the range of hundreds of microns in size, and we hope within a 5-year time to actually be able to get up to wafer scale. So what would be possible with wafer scale structures? So I told you at the beginning we had this ambitious goal of going to 20% of light speed using this enormously powerful laser that's never been built before with a 10-meter light sail. And that seems like a very ambitious, in fact, forbidding objective. But what could be done? And so it requires very high power to get to 20% of the light speed. It requires a large meter-sized sail. But let's ask the question, what would be required to get to exceed the velocity of the fastest spacecraft that we ever produced? So the Voyager spacecraft are among the few human objects that have ever moved out into the tropopause, into the interstellar medium. To do this would require light sails with about 0.1 meters, 10 centimeter diameter, would require lasers with powers in the range of about 100 kilowatts. So there are now lasers available in many places around the United States, at the National Institute of Standards and Technology, the Air Force Research Lab. In fact, you can go to a welding company that cuts parts and they have 50 kilowatt lasers. 10 centimeters is the size of a wafer. I can make it a clean room. So using these structures, we think that it will be feasible within a few years' time to create, launch, and propel a spacecraft that can move at velocities greater than the fastest chemical spacecraft. We think that is a very interesting first objective, and that plots a course for how you might go further than that. So I'll just say thank you to the team that played a role in this, and just say that we've gone here from atomic scale engineering to interstellar travel, and harnessing the opportunities in nanophotonics. So thanks very much. I enjoyed being here.
Do we have any questions for Harry?
Your wafers look very delicate. How are you going to get them up to? Should I come up?
I guess they're recording this, so go ahead and grab the microphone.
Here, I don't know. Okay. Hello. Your wafers look really delicate. How did you get them out to space and open and such?
Okay, so what I imagine is that we will deploy these spacecraft in orbit. And of course, then it means getting them from the Earth to low Earth orbit in this form. We're working now with silicon nitride. How many of you have ever worked in the laboratory with silicon nitride? Any graduate students here work with silicon nitride? Membrane material? Okay. So I can make a membrane, we've done this in the lab, of silicon nitride that's 100 nanometers thick, and I can drop a quarter on it from about a foot high, and it won't break. And the reason is because it's this beautiful amorphous material that doesn't have any cracks in it. If you work really hard, you can break it, of course, but it's pretty robust. Furthermore, what we will very likely do is to back it with a material that can be ablated away by the beam as it first, like a polymer material, something that can be ablated away so that we then have the remaining inorganic structure that gives it some mechanical backing so it survives the launch.
You talked about doing imaging and spectroscopy, but how does it communicate back? Because what good is it if we can't figure out what it's actually seeing or
Yeah, you're bringing up another of the challenges. That will require a communications protocol and scheme using what we imagine as a laser communications protocol. And so if you now ask what are the optical powers that you need in order to do this and to develop using say a detector array that is maybe the size of the phased array laser itself, which we might imagine co-locating detectors of the laser. So then if you look at the signal that you get from, say, a watt-based solid-state laser, a CW watt-based solid-state laser, perhaps operating in a pulsed mode, you can get above the thermal and shock noise detection limits of today's detectors. So we think that laser communication will be the right way to do it. There's still, of course, an important issue of pointing, so not all those problems are solved, but we think laser comm. So in fact, NASA is already beginning to deploy laser communications for its satellites, and telescope arrays in space. Yeah, follow-up question?
So I'm just, I don't know, is this working? Okay, I'm just trying to summarize in my mind the takeaway points from your talk. So one is we could send little wafer spacecrafts, not big spacecrafts of people, but wafer spacecrafts to do science to other stars in a relatively short time. The other one, I think what you're saying is we can make fossil fuels without fossils. Is that the point? We could capture carbon from the atmosphere and make methane and ethanol and things with that?
That's the goal, yeah.
And then there was a third one that I missed. So is there something about the infrared laser?
Yeah, well, really the thing that unifies all these is the concept of nanophotonic design.
Sure.
So that's really to illustrate the diversity of this field, which I think is the thing that's, the reason this has gone from when my good friend Mark Stockman and I started in this field, there were probably half a dozen or a dozen people at the conferences that we would go to, and now there are literally thousands of people worldwide working in this area. So I think it's a very interdisciplinary field. So that's kind of the thread that runs through the talk. I tried to give something that would, but with respect to the infrared, so I think the takeaway message there is that somewhat unexpectedly we saw a source of non-thermal, non-black body emission coming from graphene that we can attribute to plasmon emission, not plasmon absorption, but hot carrier generation of plasmons.
I missed it, but at one point in your talk you said we were going to use this laser that had never been built before to power this.
Yeah.
How are we going to build that if it hasn't been built already?
Well, so there is a team that is already working on the phased array laser. And the phased array laser consists of coherently coupled individual lasers. So once there are two problems to solve. One is the phase and the amplitude noise, which determines how coherent the array can be. Once you have addressed that, if you've adequately addressed that, then the next challenge is the engineering challenge of building a large array. So the lasers themselves are they're compound semiconductor solid state diode lasers. They're materials. If you look at, for example, electronics over the last 40 years, we've gone down 7 orders of magnitude cost reduction in the cost per bit of computation. Laser, if you look at the emitted power per watt, it's gone down about a 2.5 order of magnitude drop in cost of lasers. And as lasers become more widely manufactured and used, we can anticipate a similar sort of Moore's law curve for the cost reduction of lasers. So that's sort of baked into the idea that you could do this for a price tag that would be affordable. But it uses, so the key scientific challenges are phasing all of these lasers together. And there are examples of phased array lasers that are small phased arrays, but not at this scale. So there's the team that's working on this, also from Breakthrough Starshot, has already built several physical prototypes and demonstrated things at the scale of tens of centimeters, sort of a fraction of a meter.
Really interesting talk, thank you. The state can be made light, but can the payload also be made lighter?
Well, it depends what you would like it to be.
So you showed an animation where the sail goes across the planet taking photos, taking images of the planet. You need sort of an instrument to do that, and won't that add on too much weight on the sail?
Well, so the premise is that we already have lightweight imaging instruments. So the star chip that I showed you, that was an actual photograph of an instrument that weighs about 1 gram. That's already been built. It's already been produced. The only thing that weighs slightly more than 1 gram at the moment is the power source for the chip. You have to work hard on that one.
So I wondered if I could ask a question. So I know we fire lasers at the moon right now, and just through regular diffraction, the spot sizes at the moon are like tens of meters. So would that be a problem in getting the right power density to the?
So one of the things that defines the point design that I showed you, there are many possible ways to design this, is the laser wavelength. The diffraction limited resolution depends on the ratio of the aperture size to the wavelength size. So that's one of the important determining factors in the laser wavelength, about 1 micron, and the aperture size of at least 100 meters. So that you end up with a diffraction limited beam spot that is equal to the size of the sail at the end of the propulsion period. So it's about 180. So the idea is that that aperture size will now allow you to have a focal spot size of 2 square meters at the radius of the Mars orbit.
Okay, go ahead.
I have a question as far as your rebounding. I know that you're talking about the dynamics of the wafer. Is that going to be autonomous as it goes out?
Yeah, that's a very good question, actually. It has to be autonomous because once you get going to relativistic speeds, there's no time for communication back and forth. So that's why we worked hard to think about how we could build a passive stabilization scheme for the propulsion. So yeah, it's a very important question. Yeah. Everything has to basically do it by itself in a very simple and passive way.
Earlier you talked about the energy powering the microchip that people use. Did you have any ideas on how you would do it? Because batteries are heavy. I don't see solar panels people on it. It'd be kind of weird, right?
Well, you could use photovoltaic power from the star, from Alpha Centauri or Proxima Centauri. That's possible. There's sunlight at the planet, Proxima b. That's one source. Another might be thermoelectric generators, because the sail moving at that speed is expected actually to have a thermal gradient across it. We may be able to harvest power that way.
The design for the passive redirecting thing looked kind of like a piece of Lego. Would it actually look like that, or is that just sort of imagining, just a kind of?
That's because I drew it at the scale of a sort of optical, of a cartoon image. Each one of those elements is sub-wavelength in scale. So we can fabricate those in the lab using nanolithography. But all those are, you'd have to look at an electron microscope to see them.
But would they be little bumps like that? Would they actually look like that?
Yeah, that's what they look like. In fact, I didn't show them in my talk, but we've actually fabricated some already in the lab. And we're actually starting, a student who's started experiments last month, levitating little silicon nitride objects in a more vacuum stage in the lab.
So space radiation, particle radiation can be intense, especially if you're close to the stars. So how do you make your devices on radiation hard?
That's a good question. I guess the question is, how close do we have to go? We know about the radiation coming from our star, the sun, and it may very well be that another source of radiation has to do with the fact that stationary particles in the interstellar medium are going to effectively impact the sail at the sail velocity, and that is another source of radiation damage. In fact, we're a lot more worried about that than we are about, say, the radiation from Proxima Centauri. So for that, that's really an unknown, to be honest. We have my friend Avi Loeb, who's the astronomer at Harvard on our team, calculates based on stellar observations the interstellar medium density and the particle density, but we don't really know, and we're going to have to do some experiments. We have to send some spacecraft out there to find out.
And silicon especially is very easy to manage.
Yeah, that's right. Yeah.
I want to ask about longitudinal coherence of the laser radiation. You can perfectly phase them at the given level, at the surface. But they'll start propagating. And the longitudinal coherence is finite, so at some distance, they become coherent beams. Are not getting diffraction, limited radius, and intensity will be much less. What is known? Do you have enough longitudinal coherence?
That's a good question. I guess we need to, I would say we don't know the answer to that fully. That's an important question. Essentially, we want to be able to characterize the wavefront across the entire journey.
Three-dimensional spaces.
Yeah. Any other questions? Oh, sorry, still many questions.
This work. First of all, great talk. Thank you so much, and also congratulations to you and your teams that world record for the photosynthesis. That was great. But I think I missed why your efficiency rate is different with your theoretical rate. I saw that your theoretical rate of your material, I don't remember very well, but it was 85%, but you achieved almost 20% rate, and I want to know why.
Okay, yeah. So what does that mean? So 20% of the incident sunlight went into the the efficiency that I'm talking about is the so-called Shockley-Queisser efficiency. So you assume that a semiconductor is going to absorb photons above its band gap with 100% probability. You assume it doesn't absorb below. And if you look at perfect materials and you look at the solar spectrum, you don't get 100% efficiency because, for example, some of the photons are not absorbed. Some of the photons, you lose some of the energy because the photon energy is greater than the band gap energy. So you lose that energy as heat. So in consideration of all of those things, the limiting efficiencies are in the range of mid-20s%, okay, for the, so we're currently at 19.3%. So that it's the relative to what would be your entitlement from the broad spectral distribution of sunlight.
Okay, so I have two questions. The first one would be more efficient to build a laser array outside of Earth's atmosphere?
It might be more, might make everything cleaner, but a decision was made early on in the process to locate it on Earth for two reasons. Number one, the launch costs are very significant for launching something that big into space. And second is that Starshot has already approached many of the world's, the G7 nations and G8 nations to make sure that it abides by treaty obligations to make sure that nothing about the laser could be construed as a weapon. And if you put it in space, people become nervous that you're going to generate a weapon. If it's on Earth, as long as you have a clear sight line, then people are less nervous about this. So we imagine locating this in the high desert in Chile, where the European large telescopes are, because they have very large, very incredibly clear seeing. It's in this desert where it has not rained in 100 years, where there's very little moisture in the atmosphere.
My second question would be, would your internal components on the spacecraft even survive being hit with a laser pulse of that strength?
That's the point of doing this analysis about the absorption at the pumped wavelength, for example. The absorption has to be extremely small. So, normal absorption coefficient would be somewhere between a few percent and 1. We have to have absorption coefficients of like 10 to the minus 4 to 10 to the minus 6. So we're looking for exceptionally transparent materials, exceptionally non-absorbing materials that, by virtue of having the optical index high enough, can still generate quite a bit of reflectivity, but very little absorption. So there's a real material synthesis challenge as well.
if I could just ask you a final question. So the highly efficient solar conversion device you built, I was thinking in terms of scale up. So this is a rhodium catalyst, I believe you
Yeah.
said, and that kind of sounds expensive. So
Yeah.
scale up. And so, what do you think the opportunities are for using cheaper materials, and what kind of efficiencies might you expect?
Yeah, very good question. So the reason we used those materials is because they have very low overpotentials and they work at low pH. But to me, the most encouraging result was when we built the device and then we operated at neutral pH, the efficiency was nearly as high. It was about 1% lower. And we have hydrogen evolution and oxygen evolution catalysts that we can work with near to neutral pH that we believe will remain stable. Made of transition metal elements, things like nickel molybdenum or nickel oxide on the oxygen evolution side that are earth abundant.
And you think the efficiency will remain so high?
Yeah, well, we used those earth abundant catalysts in a lower efficiency device that was set a previous record at 10% efficiency. But to really pull out all the stops, we used these precious metal PGM catalyst materials. But I think that won't probably end up being the biggest check on efficiency. It'll be other engineering challenges.
Any questions?
So a question, thanks again for your talk, it's very, very interesting. I'm not completely certain where the, 20%, well, I mean, I know that 20% of the speed of light is a goal, but like, I'm not entirely sure why that might be like a limit or something like that. So I'm just thinking if you just make a bigger laser array where you can generate more energy, wouldn't you be able to go, like 60% or something like that?
Yes, well, actually, it turned out that we had a lot of discussions about that early on in the project. And as a result, we built a very large Excel spreadsheet that calculates the cost financially in dollars of building any given system at any given point design. And our philanthropist said you have a limit of $10 billion. That's all he has. But seriously, if you think about large science projects like CERN or ITER or things like that, they're sort of that scale of project, and it wouldn't be possible to go to get sort of substantial support to build something bigger. So, and so that was set as a goal that seems like it might be achievable.
Any questions? Well, if not, let's thank Professor Atwater for